Thanks to all this preparation so far, now we are ready to understand when the elliptic function field that is well rounded. So to understand when you recall the definition of the well roundedness, we want to say that like the lattice contains like many like linearly independent vectors, but we will say a stronger version. But first, we need to see that it should contain like rank many vectors. These vectors are of the minimal length. So this is why first we need to understand the minimum distance of our lattice. And in the first case, if we suppose that n is bigger than or equal to 4, actually I confused the notation. This is going to be capital N. So if we suppose that our n tuple contains at least 4 many rational places. In this research paper, by the way, they studied only with the rational places. And I highly recommend you what happens when you work with higher degree places. But I mean, in this case, if we have at least 4 rational places in this n tuple, then the minimum distance of our elliptic function field lattice is 2, and the minimal vectors are of the form of p plus q minus r minus s, where p, q, r, s rational places in P and they are distinct, and they satisfy this equality with respect to elliptic curve addition, or the addition on the set of rational places. And by the minimal vector, what we mean is just we use the notation. We have the z here, and we have the image of phi z. So here, what we mean, these are the principles. So we are talking about z in this form. We use the divisor representation. And if n is equal to 3, then the minimum distance of our elliptic function field lattice is square root of 6, and the minimal vectors are of the form plus minus p plus q minus 2o plus minus p plus 2q plus o, and plus minus 2p plus q plus o. So in this case, what we mean, p only contains p, q, and o. So we have triple here. So for the proof, first recall that p minus q is principal divisor if and only if p equal to q. And if we recall that for any function f or any function z, yesterday we introduced its degree as degree of its zero divisor or the pole divisor. Then its degree cannot be 1. Otherwise, we know that f will be elliptic. It tells us genus should be 0, but by the definition, we get a contradiction. Genus should be 1. So first, assume this case. Suppose that we have at least 4 distinct rational places. Then there are we can consider 2 distinct rational places inside of P indeed, both not equal to O. And let me suppose that P is not equal to the additive inverse of Q. Then P plus Q is equal to R. So if P is not additive inverse of Q prime, so R is not going to be the identity. Then again, just consider the function which relates P and Q. Its principal divisor is going to be minus P minus Q plus R plus O. So we know that this FPQ has the support as a subset of P, because we suppose that we have P, Q, R, and O, at least, in this intuple contains these places. Then when we look at its image under phi, we can see that minimum distance should less than or equal to 1 with respect to the L2 norm. We are just looking at the image, so we have -1, -1, 1, 1, and the 0. On the other hand, yesterday we have proved that the minimum distance is bigger than or equal to square root of 2 times the gonality. And the gonality of the elliptic function field is 2, because it cannot be 1, otherwise it will be rational function field. And we know that it has extension degree over the rational function field FQ exceed 2, because it's the degree of the pole divisor. So it is bounded below 2, hence we get the minimum distance as 2. Now let me consider the minimal vectors. In our function, elliptic function field lattice delta P, then we must be of the form of, by Abuse notation, P plus Q minus R minus S. This is going to be principal divisor, right? Because for the OP star, we know that if this is principal divisor, suppose that it's the principal divisor of Z in the P plus Q minus R minus S. So we are by the V, what we mean, it's image under phi. Here P, Q, R, S are distinct. Then P plus Q, and let me suppose that, let me also check the addition P plus Q, and let me denote it by R1. Then by the definition of this addition, we know that P plus Q minus R1 minus O is also principal, right? Then P plus Q R1 minus O, if you look at the difference of this principal divisor and this principal divisor, is in this form. And now by using proposition 2.1, we can conclude that R plus S equal to R1. So this is also principal, right? So the minimal vectors, so we can conclude that the minimal vectors inside of our elliptic function field are of the form of P plus Q minus R minus S, where P, Q, R, S are the distinct, and P plus Q is equal to R plus S. When we have only 3 rational places inside of P, so we are in the case P, Q, and O. If this is the case, and if we suppose that this is the all set of rational places, by the way, by using the a group structure of the set of rational places, we can see that this is of order 3. So Q in the form of P plus P. And the following vectors, like 3P minus 3O, 3Q minus 3O, 2P minus Q minus O, P minus 2Q plus O, like these are the vectors inside of our elliptic function field. That is because we are considering also the 3 times of the vector of this image, but this is not principle for sure. But I mean, we can say that we can check the let's say Riemann spaces, and we can say that these are the vectors in the function field lattice. So their Z combination is also lattice vector, right? Let's say A1 P1 B1 Q plus C1 O is also lattice vector. So A2P, B2Q, C2O is also lattice vector. Then in this case, we can write with such a lattice vector as we can view these coefficients. A2 should be A1 in modulo 3. B2 should be V1 in modulo 3, and C2 should be in the form of A2 minus B2. And the shortest vector then can be obtained, like the shortest vector with respect to the L2 norm, can be obtained when A2 equal to B2 equal to 1 and C2 equal to minus 1. And then when you look at its image under phi, and again when we check the minimum distance, we can see that this minimum distance is square root of 6. And finally, we can conclude that if the set of rational points in the elliptic curve, elliptic function field has at least 5 points, then its lattice structure is generated by its minimal vectors. This is a stronger condition than being well-rounded. Automatically, we can conclude that elliptic function field lattice is well-rounded. And by the theorem 2.3, we know that the lattice delta P is generated by non-zero vectors of the form of minus P minus Q plus R plus O, where P plus Q is equal to R. So in this case, it is sufficient to show that each such vector can be written in terms of the minimal vectors, right? And suppose that V is not minimal vector. So that means suppose P, Q, R, and O are not all distinct. And on the other hand, V is a principal divisor, right? V is a non-zero principal divisor, we can get a contradiction that P or Q cannot be equal to O. Similarly, this cannot happen when P equal to R or Q equal to R. So we should have P equal to Q or R equal to O. And when P equal to Q, then we in the form of minus P plus R plus O, and P plus P is equal to R. And by the assumption, we know that the set of rational points, or the curly P we fixed in the beginning, has at least 5 points. We can choose any rational place such that U is not the identity P or P plus P or minus P. Now let me put as P plus U, and let me observe that minus 2P plus R plus O can be arranged as minus P minus U plus S plus O minus P plus S minus R minus O. And now we can claim that this minus P minus O plus S plus O, or actually, and like, because we want to write this vector as a combination of the minimal vectors, right? So our claim is that this and this are minimal vectors. And by the choice of U, which is different from P and O, we can also observe that U should be different from them, or otherwise P equal to identity. This is not the case. And indeed, this S should be different from than P. Otherwise, U is infinity, but we know that we choose U different from than the identity. And finally, S cannot be O, because otherwise P plus U is O, so U is minus P. Again, it cannot be by the choice of U. Thus, minus P minus U plus S plus O is a minimal vector, because all of them are different from each other, and P plus U is equal to S. And similarly, let's observe that P plus S, 2P, P plus U is equal to R plus U. So by using the definition of this equation, we can say that P plus S minus R minus U is a lattice vector. So this is principal, and its support in the P. And we already suppose that P, S and U are distinct. So we have to show that neither S or U equal to R. And we can prove it by the contradiction, because if R is equal to S, then U is equal to P, which is not possible by the choice of U. If R is equal to U, then U is equal to R 2P. Again, this is not possible by the choice of the U. So again, P plus S minus R minus U is a minimal vector. And for the case of when if P equal to Q, then V is a difference of two minimal vectors. So this is what we have shown. And now suppose that R is the identity point. So V should be in the form of minus P minus Q plus O, and P plus Q is identity. And again, since E contains at least 5 rational places, we can consider another rational place U, which is different from them O, P, Q, and 2P. And again, by the similar setting, we can see that it can be written as the difference of two minimal vectors. So in this case, by showing that if V is before any vector, if this can be written as a combination of two minimal vectors, obviously it is spanned by the minimal vectors, and automatically this is well rounded. And then in the next following videos, we will focus on the what we can conclude for the hyperelliptic function fields. But I mean, we will give actually this was kind of natural question. If elliptic function field lattices are well-rounded, people ask the similar questions for the different function field lattices, for instance, for the Hermitian. And it was kind of natural question when a function field lattice is not well-rounded. And it was answered in 2016 in the general setting, and hyperelliptic functions field will be the spatial consequence of this general setting, and we will see it soon.